Good afternoon. I'm Chenhao Jin. I'm an assistant professor in physics at here. And today I talk about our recent progress in studying of excitations in MATBG. So I suppose I should start with the introduction of MATBG. But since I clearly am not the best person to give this introduction here, I will skip that introduction. I will start from a different system. Okay. So, well, this is a phase diagram which is famous, is classical, and we are all probably familiar with. And it has profound impacts in condensed matter. It has motivated numerous studies in many-body physics. But after decades of studies, this phase diagram is still not fully understood. So naturally, we can ask, why is that the case? And I'm an experimentalist, so I would like to identify some challenges from the experimental point of view. So these systems are great. They have a rich phase diagram, and they show a high TC superconductivity. But at the same time, they are also complicated, and they are quite dirty. We know that all these systems, they can have a lot of disorders at the lattice scale, and that makes it difficult to extract intrinsic physics, as well as to model it in theory. They are also not that easy to tune. We have tuning knobs like pressure or magnetic field and chemical doping, but they are all not that convenient, and also limit the parameter space we can access is kind of limited. And besides this, more practical challenges, there's also an intrinsic challenge. So there are many different phases, different orders in this phase diagram. And that's great because there are rich physics here. But it's also making the phase diagram quite complicated because there are so many different orders and fluctuations. And in many cases, these fluctuations will compete with each other and they won't develop into long-range orders. Experimentally, it is much easier to probe long-range orders because, well, they will survive through all the average, either in space and time. But if long-range orders are not developed, it's typically much harder to know what is happening. And so here are the challenges. So what are the solutions? The solutions to the first two challenges are all straightforward. We can try to find a better system. If they are dirty and complicated, let's try to find a simpler and cleaner system. If they're hard to tune, let's try to find a more tunable system. But how about the competing orders? So can we find a system without competing phase? That's actually not an option because this competing phase could be intrinsic to the physics we are interested in, such as the emergence of unconventional superconductivity. So we actually want to keep the competing phases and keep the complex phase diagram. And instead, what we can do experimentally is try to improve our experimental capabilities to try to understand what's happening, even if there is no long-range orders. For example, we can try to directly probe fluctuations even before they develop into long-range orders. And over the past several decades, there have been tremendous progress over these different directions. And one of the recent breakthrough is the discovery of superconductivity in flatband graphene systems. So there are many different systems. So I just take one representative phase diagram here. And these systems actually can address two of the three challenges pretty well. They are not that simple, but just from the lattice, they're pretty simple and they're clean. There's a single carbon element, and there's a single pz orbital, and they can, in principle, have perfect lattice. They're also quite tunable. We can continuously and conveniently navigate through the phase diagram just simply by gate voltages. And we can realize many different intricate phases in a single device. So how about the third challenge? So the phase diagram is also quite rich. There are many different orders in it, which is both good and bad. The good thing is, well, it seems that the physics here could be very rich, and it could represent the manual physics we want to study. But also, it brings the same challenge as in the conventional systems. And we can ask, how do we probe fluctuations here? Because, again, long-range orders may not develop. And of course, to answer this question, we should first ask what are the relevant orders and fluctuations in these graphene systems. And it turns out that one particular important order or class of order is the so-called isospin orders and textures. So here the isospin means spin and valley. So we know that in graphene there are all spin and valley, this degree of freedom. And then we can have many different orders or textures in this isospin degree of freedom space, such as like a spin or valley polarized state, intervalley coherent state, etc. And here is some examples in different graphene systems. So in the moire graphene systems, these isospin orders typically emerge around integer fillings, and we can see a set of cascade features near integer fillings, which has been associated to the isospin orders. And in non-moire systems, such as Ramakrishna graphene, they're actually even more prevalent. They are appearing in a large range of the phase diagram, so they're almost everywhere. And these isospin orders, they are important, not just because they are everywhere, or that's one of the reasons, of course, but also because they seem to have some connection to the superconductivity. If we check the domes of superconductivity in both moire and non-moire systems, it seems that they typically emerge near the transition or near some of these isospin orders. And this motivates us to think that probably these isospin orders could be a common string connecting the diverse phase diagrams of all these different graphene systems. And also there could have some connection to this superconductivity. And indeed, recently there have been widely proposed that these isospin orders and transitions could play an important role in the emergence of superconductivity. So it's pretty clear from these titles. So in particular, it has been proposed that the isospin fluctuations can play an important role, such as provide a parent glue for the emergence of superconductivity. So now our question can be more specific. We can ask, how do we probe these isospin fluctuations in flatband graphene systems? Of course, here isospin order and fluctuation is kind of a general term. So there are many more specific orders and fluctuations could be there, belong to this general term. And here I'm just giving some examples. So we can have quite a few different orders, including both polarized orders and coherent orders. So we can take an example of this specific IVC order or intervalley coherent state, and we can ask, how do we probe the fluctuations associated with this order parameter or this IVC order? So we can think about what's the typical way experimentally do we probe fluctuations in condensed matter. So typically there are two ways. So one is scattering, the other one is stability. But both of these two ways require we directly couple to the order parameter. For example, if we want to do stability, we have to drive the order parameter and see to couple to it and see what's the response of the system. But it's unclear how we can do it here because some of these order parameters are quite exotic, and it's unclear how we could couple to them. And in addition, scattering measurement is just generally hard for 2D layer. So they are very powerful for studying bulk systems, but cross-section is just too weak, too small for a small and thin 2D layer. So it looks like our third challenge is actually even harder or even more serious for these flatband graphene systems if we want to probe fluctuations. And this motivates us to ask, is it possible to probe fluctuations without directly coupling to them? And the answer is actually, well, at least in principle, it's possible. So the reason why stability can be used to measure the strength of fluctuations is because of the fluctuation dissipation theorem or linear response theory. So this tells us that when there's strong fluctuation of a certain order parameter, then, well, if you drive it, the response will be very strong. It also tells us what strong means exactly here. So if you have a strong fluctuation, it really means that, well, there's a large correlation length and time of the fluctuation. And that can be intuitively understood because, well, if the correlated time and length are long, then that means the response is contributed by the driving over a large length and time scale, which may make the response very large, which means a large stability. So this actually, well, there's an interesting implication here. So of course, large correlation length and time are also connected because, well, if the correlation length is large, then all the large region of the system have to fluctuate together, so it cannot be very fast, it has to be slow. So this tells us that, in principle, we can actually, well, try to probe some important properties of the fluctuations from the time domain, because a strong fluctuation will intrinsically give rise to a slow dynamics. And this can, in principle, of course, I'm using a single arrow here because there are many other reasons which can give us slow dynamics, like deliver on pizza can also be slow. So we have to be very careful here. But at least, in principle, this tells us it's possible to get some information, properties of the fluctuation, without directly coupling to it, because we can simply create all excitations, and the slowest one will live the longest. And this will allow us to naturally isolate the ones potentially with strong fluctuations. Okay, so some examples I guess we're all familiar with. So an extreme example is the critical slowing down behavior near critical points. So we know that because the fluctuation is very strong, so the dynamics is very slow. If you look at the relaxation dynamics of all the parameter, it becomes slower and slower if we approach the critical point. And this can be easily simulated in a 2D model. It's also observed in various types of magnets. So we can see that when we go near the critical temperature, the dynamics becomes very slow. And these systems are all relatively simple because there's a single order parameter, so the physics is well understood. But in principle, this concept could also apply to more complicated scenarios, such as a competing phase diagram. And that is the main idea of our study. So more broadly speaking, we are trying to go beyond the ground state and directly probe the properties of fluctuations by looking at the ultra-fast dynamics, isospin dynamics in particular, of graphene systems. And experimentally, how do we do it? So well, to achieve it, there are two requirements. So first, we have to be able to create the excitations at ultra-fast time scale. And of course, second, we have to probe them at an ultra-fast time scale. So the first requirement is relatively straightforward, and is standard for optical pump probe measurement. If you want to create some excitations at ultra-fast time scale, just use the ultra-fast light or femtosecond pulse to excite the system and create some excitations. So that is fine. But second requirement is not that trivial. So how do we probe isospin orders at ultra-fast time scale? Well, so one of the main problems here is that these isospin orders are at quite low energy scale, so typically sub-milli eV. So if you convert to frequency, that's 100 gigahertz or sub-terahertz. So it looks like we have to use some terahertz light or 100 gigahertz light, and which is very hard to work with. But even in that case, it is still unclear how this terahertz light would couple to these isospin orders to probe them. So to meet these requirements, we actually have to address two challenges. So first, we have to figure out a way to somehow make our optical probe sensitive to these isospin orders to be able to probe them. And then we have to do it at ultra-fast time scales. Okay, so then, well, we're trying to, question?
I missed experimentally which components of this isospin. There are many degrees of freedom.
It's spin and valley. Spin and valley. Sorry, yeah, asking. Yeah, spin and valley. Yeah, so now we're trying to figure out how to achieve these two steps. And the first step is actually not that hard. It turns out we just need to take some advantages of these 2D layers, their geometry, and play some tricks with the device design. So here is the idea. It's quite simple. So we just place a monolayer TMD such as WSE2 in direct contact with the graphene layers. So this geometry, we probably have seen it a few times in other occasions. And there are different reasons to use this geometry, such as to introduce spin optical coupling. But actually, well, here we use it. It will still introduce spin optical coupling, but that's not our purpose. Our purpose is actually using the interaction between the graphene layers and the WSE2 to encode the isospin orders in graphene into the external response or optical response in the nearby WSE2 layer. So we know that these 2D superconductors, they have a very strong external response and a very strong light-matter interaction. So basically, we are effectively using this WSC2 layer, the axon inside, as a sensor to try to sense the isospin orders in the adjacent layers. And we can call it an adjacent layer axon sensing. And I will not go into details, because that's not my focus today. So please refer to this archive paper for details. It discussed in detail why this, what's the principle here and why it can work. So why we are able to sense isospin orders by looking at the optical response of the nearby WSC layer. Basically, if we believe this works, then we can simply just measure absorption of the WSC2 layer, use light, and that will tell us the information about isospin orders in graphene layers. So here, I just use the simplest way to demonstrate the work because it works in experiment. So here, in this plot, we are seeing a phase diagram of the RTG, remote layer graphene, and from electrical measurement. And so this phase diagram is kind of is consistent with our previous studies. So we'll just briefly go over it. So we can see some lobes on the whole side and some transition on the electron side, and they are coming from the isospin orders. And so here is the same device, but we probe it with our optical sensing technique. And so we can see that, again, it fully captures all the information of the isospin orders. So on the electron side, we see two sharp transitions. On the whole side, we see some lobes. So just from experimental point of view, we can see that it can capture the isospin orders and transitions, which is what we want. And so here, the focus of the talk today is not the RTG, it's MATBG. So we also apply to MATBG. And again, it works. So here, again, we are seeing an absorption spectrum of the WSC2 layer, which is in direct contact with the MATBG. And the horizontal axis is the filling. So in all these structures, because the direct point or the flat band of graphene sits deeply inside the band gap of WSC2, so when we dope the system, we're only doping graphene, and WSC2 is always charge neutral. So that's why the 1s axon just doesn't change. But if you look at 2s axon, which is quite sensitive to dielectric environment, then we can see some rich features and these features reflect what's happening to electrons in the nearby graphene layers. Here, what we see is that there's a series of cascade features at the integer filling from -4 to +4. And that's reminiscent or very similar to the cascade features observed in other techniques. So again, this tells us that our axon sensing or optical sensing technique are sensitive to the isospin orders, and we can use this to probe what's happening to the isospin degree of freedom. It's reflection contrast. You can consider this as an absorption. Yeah. It's a way to measure absorption. Okay, so this is the first step, and next step is to bring it to ultra-fast timescale. The idea is pretty straightforward. So first, we add an ultra-fast pump light to excite the system transiently to create excitations at ultra-fast timescale. And then we replace the probe light. So here, the probe light is a continuous wave light. It's not a pulse light. But now we have to replace it with an ultra-fast femtosecond pulse light. And it's also a broadband white light. So it's a broadband white light pulse. And this allows us to obtain the absorption of the WSC2 at a given timestamp. And then if we choose the pump and probe delay, fix the delay to be a specific moment, then we can tell what happens to the isospin degree freedom at that moment. And we can know what happens, what dynamics of the isospin orders and excitations. Okay, so this idea is quite simple, but to make it work, it's actually not that trivial. So bringing everything from here to here involves significant technical challenges, which I will skip. So eventually, what we were able to do is just to make it work, and here's what we have. So let me go through this clause carefully and slowly. So here, this delta t shows the delay between the pump and probe light. So here, the delta t is negative, which means the probe light is, or the pump light has not arrived yet. So essentially, there's no excitations in graphene, and we are looking at equilibrium. And we know that at equilibrium, we should see cascade features, which is what we see here. It's labeled by the arrows. And then, let's look at a different delay. So here, This is 1 picosecond after the pump light arrives. And we know the pump will excite graphene. And these excitations can be monitored from this absorption in the nearby WC layer. And what we found is that these classic features are melted. And that's not too surprising because, well, we dump a lot of energy into graphene, which will make the electron temperature very high, which will melt all the others. And then if we look at 10 picosecond after time 0, then we can see that these cascade features start to recovery. They are not fully recovered yet, but they are recovering. And if we wait a little bit more, and at a few hundred picosecond, then it's almost recovered, so it's approaching equilibrium again. Okay, so from this snapshot, we can get a quick glimpse of the excitation process and the relaxation process. So our goal here is to try to look at the relaxation dynamics of the isospin fluctuations or excitations. So let's take a look at the relaxation process more quantitatively.
So the first diagram means that actually before you pump, like the system has the isospin order already.
Yes.
Okay. So actually kills it and then recovers.
Yes, it's melted and recovered. Yes.
Another quick question. So this isospin order is some spin and value orders, right?
Yes.
So the light that you're shining on the sample, is it circular polarized or
it's not. It's
how is it coupled to these orders?
It will melt all the orders. So that's the point. So it doesn't need to couple to the order directly because let's say if you heat the system to very high temperature, it will melt all orders. So it will create all types of excitations just by thermal excitation, for example. I mean, I'm just giving an example. So that's why you don't need to directly couple to the order parameter. You just create all excitations available in the system.
Oh, so the goal of the light is just to heat the sample up?
Well, yeah, you can think in that way. It's heating the electronic degree of freedom, which will basically create all possible modes available in the system. Yes.
Another question is, how do you know it's not coming from the WSEQ layer, but the graphene?
Oh, yeah, okay, I forgot to mention that. So basically, we use the pump light below the bandgap, well below the bandgap of WSE2, so we cannot excite WSE2. Okay, well, I'll discuss briefly later, but for now, here I'm showing all the results first. So yeah, and I think it's also not completely true that it's probably not completely true that this cascade feature is directly related to. I mean, they are related to isospin order, but they are not necessarily, just a very direct signature. I mean, for example, this is not a gap. I mean, even it's kind of a chemical potential. It looks similar to the chemical potential measurement previously, but like you can see these cascade features even above the ordering temperature. So they are not really a one-to-one correspondence with the isospin orders, but they are connected.
Maybe along the same lines, you see a feature in label 4.
Yes.
Which should just be the film back. That's not really an isospin.
Yes. Yes.
So what exactly are these peaks measuring?
Okay, so these are measuring the polarizability of the graphene layer. So they will be affected by isospin orders. They're also affected by like a big charge gap. So we will see both in this measurement. Okay, so now we are trying to look more quantitatively of the relaxation dynamics of the system. And to this end, the typical way is to subtract the background of equilibrium spectra. So basically here we can see before time 0 there's no signal because it's subtracted. So this allows us to directly look at pump-induced change or the excitations in graphene and see how it changes over time. So again, at the beginning there's no excitation, so there's no signal. And at time 0, once the pump arrives, we see a strong signal, and then it will decay over time. So we can directly see how it decays over time and look at the relaxation dynamics. And here, this plot shows a specific filling at 1.56. And so we can see that the signal disappears after about 45 to 50 picosecond. And then we can change the filling and do the same measurement. And so this is 1.77, and 1.97, and 2.18, and 2.39. So it's obvious to see that the dynamics change dramatically over this range. And in particular, we see that the relaxation becomes very slow near 2. And to be more specific, it's in the range between 1.7 and 2.4. And we can do the same thing for the whole doping side. So again, this is minus 2.8, 2.6, 2.4, 2.2, and minus 2. So again, we see all the dynamics become quite slow over some range, and here is between 2.8 and 2. Okay, so just to summarize the dynamics. So here we can do a very crude single exponential fitting to get the dynamics over the field-independent dynamics. And if we look at this summary, then apparently there are a few regions shows a slow relaxation. They are plus minus 4, and also around plus minus 2. Of course, for minus 2, it's not really around minus 2. It's between minus 2 and minus 2.8. It's away from minus 2 actually, but just for simplicity, let me call it around minus 2. Okay, so now we know the relaxation dynamics. The most important question we want to ask is, what are these dynamics corresponding to? So what's the process giving all these dynamics? And in particular, or whether they are coming from charge dynamics or the isospin dynamics. And this is a very different scenario. If it's coming from charge dynamics, then a slow relaxation means a slow cooling of the electron temperature, which typically coming from reduced electron-phonon coupling, like a phonon bottleneck. But if it's isospin dynamics, then it's more exotic. It tells us that isospin orders are recovering very slowly, and there are some long-lived isospin modes in this region. So fortunately, we can directly answer this question because there's a previous study which already measured charge dynamics in MATPG. And they used the ultra-fast photovoltage measurement. And we know in graphene, the photovoltage is mainly contributed by the thermoelectric effect. So if you measure the dynamics of the photovoltage, that's directly a charge dynamics, and directly tells us how fast the electron cooling is, and there's no information about isospin degree of freedom. But in our measurement, we know, as we have seen, that it's sensitive to, isospin orders as well. So we are looking at both charge and isospin dynamics. And so we can directly do a comparison between these two plots and see which peaks are from charge and which peaks are not from charge. So in this charge dynamics, first what they see is there's a slow relaxation around plus minus 4. That's not surprising because there's a gap there between the remote band and the flat band. This should give a phonon bottleneck. And we also see this slow relaxation around plus minus 4. And again, it's probably not surprising. It tells us that it's most likely just a slow cooling of the electron temperature or slow charge dynamics. However, if you look at all the regions between plus and minus 4, then the charge dynamics is actually very fast throughout the whole region. And actually, the main conclusion of this paper is that the charge dynamics of the electronic cooling is accelerated in this whole region because of the Oakland process involving moire phonons. So electron cooling is very efficient over this whole region. It's more efficient than non-twisted ballet graphene. But in our case, we actually see very slow, even slower relaxation at plus minus 2, around plus minus 2. And that means that this direct comparison tells us that this cannot be coming from charge dynamics, and most likely it's from isospin dynamics. And another thing it tells us is that at this point, the charge and the isospin dynamics are completely isolated, decoupled. So supposedly we should be able to directly see their decoupling in our measurement. And indeed, we can see their decoupling directly. So here we are seeing a full dynamics at around minus 2 filling and around 4 filling. So at a glimpse, we can probably already tell that this dynamics looks qualitatively different. But it's more clear if we just compare their decay dynamics directly. So here the blue symbols are at 4 filling, and we can see that it's very well described by a single component with about 60 picosecond lag time. But if you look at the 2 filling, or around 2 filling, it's given by this blue symbol, the red symbols, then apparently it cannot be described by a single decay component. There are 2 well-separated components with 10 picoseconds, the fast component, 300 picoseconds slow component, respectively. And similarly, on the whole doping side, the minus 4 is also a single component, but minus 2.3 is 2 components. And this fast component is matching pretty well with the charge dynamics obtained in the other paper. but this slow component is much slower, it's completely decoupled. And the complete decoupling between the charge and isospin dynamics can also be confirmed from the pump fluence dependence. So here we are changing the intensity or the fluence of the pump pulse. We change it by 4 times, so it's a pretty big range. And this will significantly change the initial electron temperature, and it should change the charge pooling process significantly. And indeed, we found that the initial fast component is changed significantly if we change this pump fluence by 4 times. However, this slow component doesn't change at all. So this not only tells us that, well, these two dynamics are completely decoupled, but also it tells us that this slow component, this at long time scale, actually does not depend on how we excite the system. So it's also gives us intrinsic information of the system instead, and doesn't depend on how we excite it. Okay, so then we can take a closer look at this this slow decay around ±2. So I have measured 3 devices, and they are slightly different in twist angle and slightly different in the behavior. But the consistent behavior we observe is that there's a quite slow relaxation. On the electron side, it's around -2, +2, or sometimes slightly above. But on the hole side, it's always between -3 and -2. It's well away from -2. And we also have a device the third device, which can directly allow us to compare transport and dynamics. And this in transport, it's not that surprising. It's quite common. So we see a strong peak at 4 and some weaker peak at the integer filling 1, 2, 3. Our temperature is pretty high, it's 2.5 Kelvin. So these peaks are not that impressive, but they're there. And we can directly see that the whole side, this slow dynamics, actually is between 2 and 3. It's well away from the insulating state and -2. And this is actually a very interesting filling range because there are several other interesting observations happening at this filling range. In particular, in both MATBG and MATDG, IBC orders have been probed from STM measurement. And so here is a plot from these 2 papers, which shows us the strength of the IBC orders as a function of a filling. So the top is the filling. And this can be identified from the Kavli peaks in STM, the Fourier transform of STM. And we can see that on the whole side, it actually, there's a strong IBC order between -2 and -3. And on the electron side, there seems to also be some IBC order near +2. So that's kind of interesting. They seem to match pretty well. And another interesting observation, which is quite often in all our reports, is that symmetricity seems to be most widely observed in this range. Since there are so many reports, I just pick one which has the closest device to us. So here we have a 0.95 degree MATBG with WSC2, and this device is a 0.97 degree MATBG with a WSC2. So again, we can see that symmetricity is between -2 and 3. Okay, so I just need 1 more minute. So, okay, before I try to make some conclusions or implications, let me just show the final piece of experimental data. So we also did temperature dependence. And so here, from 2.5 to 10 Kelvin, the dynamics. And at ±4, it doesn't really change over this range, which is not surprising. But at ±2, it first changes significantly, which is probably also not that surprising because they are associated with the isospin orders and fluctuations. But what's probably more surprising is that this slow relaxation is still remains there, although much weaker, but still there at 10 Kelvin. And this is the temperature is pretty high already. It's supposedly well above the ordering temperature of any isospin orders. Okay, so at the end, let me give a quick summary first. So our main observation is also slow isospin dynamics at these 2 regions in the filling -3 to 2 and 1.8 to 2.4. And the most surprising one is probably the weakly damped isospin soft modes in the metallic state between -3 and -2, and which is an interesting region. And also, we also find the damping remains relatively weak at elevated temperatures, which is quite unusual. So we're still working and trying to understand this observation. So if you have any idea, please let us know. Any input would be appreciated. So here are just some relevant thoughts. So we found that there exist weakly damped isospin modes in between -3 and -2, and they can naturally give rise to strong fluctuations because they're not damped. And so it's possible there's some strong isospin fluctuations in this region. And interestingly, they have been indeed proposed to provide a pairing glue for superconductivity. And besides, because we find that this slow relaxation or this modes remain weakly damped up to some temperature above the ordinary temperature. So our results may also could have some implication on the previous measurements on elevated temperatures, such as the Bernschuk effect or linear in resistance, in temperature resistance. Okay, so at the end, broadly speaking, our hope is that our measurement can go beyond the long-range orders of the ground state and provide some new information of the fluctuations and excitations from the dynamics. And this could help to establish a complete picture of both orders and fluctuations, and to help us understand this interesting but challenging phase diagram. Okay, so I'll stop here. So before I finish, let me thank everyone who contributed to this work. Thank you.
So what can you say about the nature of these fluctuations? What is your probe really sensitive to, if it's not charge fluctuations?
Yeah, so our probe is sensitive to generally isospin orders. So yeah, the reason, if I want to briefly comment, is that isospin orders will reconstruct the Fermi surface, and which will change the polarizability of the graphene. And so basically, what we are looking at here, the external response is sensitive to the dielectric screening or the dielectric environment. And so when the graphene polarizability change, it will have effects on the external energy. So we're looking at that. But the details can be found in that archive paper. So, but in short, generally, we are sensitive to all kinds of isospin orders.
But if you're measuring like dielectric, some density response, why does it not enter at all into the photovoltage measurements that you mentioned?
That's a thermal effect. So that photovoltage measurement is a thermoelectric response. Mm-hmm. So it's just depending on electronic temperature.
Okay.
Yeah, so I wonder whether you can see any like SU4, SO4 symmetry from your measurement at all, or?
So are you asking whether we can infer some the ground state or some?
No, just well, I mean, so this mode should encode some of the symmetry, right? So,
yes.
So for example, should have some degeneracy due to the symmetry. You know, so I wonder if you break the symmetry manually, whether you split the modes into more modes or something.
Yeah, that's a good question. Yeah, so indeed, so if we change the symmetry and the energy of the mode should supposed to change a lot, I mean, depending on what the mode is, and also the strength of fluctuation, also the dynamics, the damping should also change. And yeah, but yeah, something we're trying first, but also. Yeah, I guess the simplest way is to apply magnetic field, which we are trying. But also, if you want to change some other symmetries, it's also not that easy.
Is a strain can
sure, I mean, yeah. Sure, yeah. I mean, so there are something which, in principle, one can do, but in practice, it's a bit hard to control. So, but yeah, that's certainly something we are trying.
Any other?
Can you say a bit more about the temperature dependence? You said elevated temperature, but
yes.
Do you have a graph as a function of temperature, the lifetime or the size of the signal, or what do you mean by elevated temperature?
Oh yeah, so okay, we don't have a very complete, because this takes a very long time, each of the curve. So we only did this for temperature. And so if we look at the, yeah, okay, so I wouldn't draw any very quantitative conclusion based on this plot, but the qualitative behavior is there. So the qualitative behavior is first, I mean, the dynamics becomes much faster, but also it's significantly still slower than the base here, such as at 1 filling and 3 filling. So basically, that's a qualitative conclusion. We are confident, but the quantitative, like for example, if you want to make a scaling with temperature, yeah, that's. We are trying to do things better to be more quantitative, but it's a little bit hard just from what we have so far.
Any other questions?
if there was just a spin order, some magnetism, that does not enter the just dielectric polarization. So would your probe still be sensitive to that? And if yes, how?
Yeah, so you're asking if it's a spin polarization, right?
Spin polarization or orbital?
Yeah, sure. I mean, if we consider, again, I suggest you to refer to the other work. So if it's a spin or valid polar state compared to a non-polar state at all, the Fermi surface is different. And then the polarizability of the graphene will be different. And so just, there are also some calculation from our collaborator which show you will be able to see it. But as a generally speaking, so all this, if you change the texture or change the polarization or change the, just change the different orders in the spin valid space, it will change the polarizability of the graphene. So if you have two copies and you only have one copy, it will be different, the Fermi surface.
So you're really sensitive to like change in electronic dispersion or something like that, and even in the insulator, because you see it in the insulating states, right?
Okay, so yeah, I mean, if there's a big gap, of course, I mean, we are seeing the polarizability. If there's a big gap, then well, it's a big insulator. If it's a vacuum, for example, there's no charge in it, and it won't screen anything of the extron in WSC2. So yeah, when there's a big gap, we also see it. But I mean, well, okay, if you want to, we can probably discuss later. So it's kind of more sensitive to isospin orders than a single particle gap. And the reason is a bit complicated, which we can discuss later. But in general, it can have sensitivity to both, but it's more sensitive to one type than the other.
Any other questions?
I have a quick question, actually. So because WSC2 is nearby, do you think that there is a proximatized spin coupling?
Yes.
If there is, then maybe shining a circular polarized light will help you directly couple to degree freedom, right? And then that will help you.
And we have tried that. Okay, so we have tried in both. So we both tried to use it to inject some spin polarized carriers into graphene. We also try to see whether we can use circular polarized light to actually couple to some of the orders. So up to this point, we haven't seen clear effect from using circular polarized light. But yeah, we're still trying.
Okay, I see. Okay. Oh.
Have you tried this technique on some other moire materials, like maybe the TMD Mott insulators, where I think we know a little better what is going on?
Yes, we are. That system is a bit easier. So we're actually trying to do a bit better than this for there. We can actually, because in that case, we can directly couple to the orders. So here we use extron sensing. So it's a kind of indirectly coupling to the amplitude of the parameter, but it's not sensitive to the sign. So, but in that case, we can, and we can also directly inject some spin polarized. Yes, we are doing in those systems as well. Yeah.
Okay, so let's thank our speakers again, and